Welcome, everyone. I'm going to tell you about a project that we're very enthusiastic about, and I think it can also help the Bitcoin community. It's an enabling technology based on a breakthrough in theoretical computer science that I want to describe to you, especially focusing on the applications to the Bitcoin community. So I'll start with some examples of the things we can do. And let's take some things the way they're done today with Bitcoin and the way we can, change it and make it better. So today when a new Bitcoin node fires up, what it does, it downloads all of the blockchain from the Genesis block, and it needs to verify all of the transactions there. If our system is used, which implements succinct computational integrity and privacy, you could do it much more efficiently. The new node that fires up just downloads the last hash, and then it downloads a very short signature that some other node verified all of the blockchain. The signature is short, let's say less than 1 megabyte. It's probably going to be on the order of several kilobytes, and it's very easily verifiable. And the important things are that this is a non-forgeable signature. It cannot be forged in any way, and if you read it and check it, which takes less than 1 second, then you know that all of the transactions were verified by someone, leading to this very last block. Another example of computational integrity. Today, if a mobile application, your cellular, reads a transaction, then it checks it with a bunch of other nodes, and it pretty much has to trust them that they verify that it's legal. Well, if you're going to use our system, then what you can do is you still check that it appears on some other nodes, but you will receive it with a signature that certifies that this node has checked the transaction. And again, the signature is going to be very short, something like 10 kilobytes, easily verifiable, even on a mobile app. And again, there's no way to cheat. Okay? Another example. Today, when you want to post a transaction on the network, on the blockchain, you're going to send it to some nodes, and they have to do all of the verification. Okay? And if someday it's going to be in a sort of a complicated script, then it's going to take them a lot of time to verify this. In the new system, if you use SCIP, succinct computational integrity and privacy, then the transaction can come with a signature that basically says the client who is posting this transaction has checked that everything's okay. And now what the node does, it just checks that the signature is okay, which is going to be very, very short and simple to do, and the nodes only need to collect the transactions and just add the proof of work at the end. Okay? And let me give just one example of privacy. Suppose I want to prove to you that I own 1 million bitcoins. Unfortunately, I don't. But if I were to try to prove to you right now, the simple way to do it is I would point to 1 million unspent coins on the blockchain, and for each one of them I would provide some information showing that I know the spending key to go with it. Okay? But then, now you know of 1 million coins that at this point in time I have in my possession, and that compromises my privacy or the privacy of my wallet. Well, if you have succinct computational integrity and privacy, here's an alternative solution you'll be able to do. You will provide a signature, I will provide to you, okay, to prove that I have 1 million bitcoins right now. What I'll do is provide you with a signature that I ran a program. And this program is a very simple one. It went to my wallet, counted the number of unspent coins I had there, verified that they are unspent, sum everything else up. If the number I get is greater than 1 million, I return to you a bit, which is 1. Otherwise, I return to you a bit that is 0. So, all you're getting are two things, a single bit and a signature. The signature is very short, much less than 1 million addresses. And it reveals no information but for the fact that the bit is correct. So you see, we didn't compromise privacy, and yet you have the integrity you need, because the only way for me to produce a signature is to actually know of 1 million unspent coins and prove them to you. Okay, so these are a few examples. And this latter thing is called a zero knowledge proof in the literature. Okay? And we'll talk more about this in a minute. So the takeaway message is that we have a new enabling technology for Bitcoin. And it is based on rather advanced theoretical computer science and cryptography. In particular, we're showing the first implementation of a succinct computational integrity and privacy system, which starts with an arbitrary C program and obtains the asymptotically best possible cost by using a lot of advanced theory that I'll just mention a little bit in the remainder of the talk. So let's take a step back and look at the broad theoretical problem that we solve, of which all those examples are just special cases, and there are many, many more. Basically, whenever you can write a program in C that you would want someone else to run, and you don't trust him, but you want to know that the output is correct, and he doesn't trust you and doesn't want to reveal any information but for the output, that's the problem we solve. So this abstract model has two players, Alice and Bob, and each one has a problem. Alice's problem is that of a lack of trust in Bob, and she wants to have computational integrity. So she starts with a program that she trusts. The program is written in C. And she wants Bob to execute this program on his computer, but her problem is she doesn't trust Bob, so how can she trust the output? That's the computational integrity problem. Bob has a different problem, because Bob is willing to execute the program and even provide the answer. But the computation, as in the case of wallets and many other instances, this computation may require auxiliary information which Bob really does not want to reveal, like his wallet. So Bob is willing to provide the output, but not the auxiliary information. How can he convince Alice that the output is correct without revealing his private information? That's his problem, privacy. Okay? And the third problem is that of succinctness. And that's really a mind-boggling one, because it seems to be nearly impossible. Alice has the program P. She's willing to spend, some time to read the program or to send it to Bob. But Alice might have her computer on a mobile app, okay? So the running time of the program is typically much greater than the program description itself, as in the case of verifying all the transactions since the Genesis block. And Alice is a mobile app. She can't run all of that. So she would like to be sure that the output is correct. But if you're familiar with the undecidability of the halting problem, it basically says that you cannot know anything about a computation without running it and executing it. So let's try to do some logic here. If Alice is going to run in time that's much less than the running time of the program, and she does not trust Bob at all, how can she trust his output? Okay? This seems to be sort of impossible. And that's why the spectacular theory that shows how to solve this problem has gotten so much attention and clout in the world. In particular, for instance, the very latest Turing Award for 2012 is going to Shafi Goldwasser and Silvio Micali for their work, for a number of works, one of them together with Charlie Rakoff on the concept of zero-knowledge proofs. Okay? And there are other amazing works about probabilistically checkable and transparent proofs, about computationally sound proofs, and all kinds of efficient versions of them, and that's the part that I've been most active in, which solve all of these three problems in a pretty efficient way. You get computational integrity for Alice. Alice can trust Bob's output. For Bob, he retains his privacy. He reveals no information but for the output. And you do this in a succinct way, which means that Alice does not need to ever execute or run a program that is more than just reading the C code, something like that. And it sounds pretty magical, and it is. When I started doing my research, my advisor back then in the early days was a professor from Hebrew University called Nati Lineal, and he told me that when you deal with a tough problem, there are usually three stages to it. First, you look at it, and then you say, oh, that's easy. After some time, you think a bit more about it, and you say, wait, that's completely impossible. And then sometimes comes the third phase, in which you sit for a long time, and maybe you solve it. So I'm hoping to get you at least to the second phase and try to impress you with the fact that this sounds sort of impossible. How can Alice and Bob don't trust each other at all? Alice is willing to, Alice has a program she wants Bob to execute, but she can't trust him. She doesn't even have the capability to run any execution that is as long as the running time of Bob. And Bob, on his side, has private information he cannot reveal to Alice. So how can they convince each other that the output is correct? I hope you see that it's sort of mystical and magical how this can all happen. Now, if you go out there, I mean, you know, Bitcoin and other things in security and cryptography are based on a lot of beautiful work from the 1970s, like public key cryptography, hash functions, and other things like that. And there are a lot of implementations and a lot of things out there that use them. If you go and look for downloading software that does zero knowledge or probabilistically checkable proofs, today you won't find it. Our point is that, you know, by the end of the summer you will. And the reason it's not been fully implemented so far for you know, just standard C or Python programs is because of efficiency problems. So while the theory and math is really beautiful and nice, it's very hard to scale it down to make a system that's working. And in particular, if you want to achieve all of these, you want universality. You want it to be something like a compiler that works for any program, not just for one typical thing that you did. And you want to have minimal costs both for Alice and for Bob. And you want to have a minimal number of interactions. You don't want some convoluted protocol that Alice and Bob send messages back and forth. You want something that's as short as a signature. You want all of those, then getting it into a working system is a big, big challenge. That's why, you know, the spectacular works about zero knowledge proofs and other things are already 30 years old, but they haven't been implemented so far. And our main contribution, and that's what I'm telling you about, is that we actually solve this sort of theory to practice challenge. There have been in the past a few implementations of parts of things, either computational integrity or computational privacy in certain settings, and there's a list of works there. I'll put also the slides online and you can check the references there. Our main advantages, the main advantages of our new system are, first of all, universality. It will start with standard C programs, you know, with loops and arrays and memory allocations and everything. And it will be succinct, so the cost of Alice will be much smaller than the running time of the program, and the cost for Bob will also be manageable. So Bob has to put some extra effort in order to generate the signature, but it will be something manageable. In particular, it's close to the running time T. Polylog means there's T multiplied by a polynomial times logarithm of T. So if T equals something like 2 to the 32, log of T is 32, and if the polynomial is something like squared, then that would be 900 times the running time, times 2 to the 32. To compare this with previous solutions, at the very least they had to run in time T squared, which if T equals 2 to the 32, that brings you up to 2 to the 64, which is a little bit worse. So, I just want to give a little bit more details on this sort of asymptotic mathematical scaling of the system. Then I'll give you some numbers of what you can expect to see in the context of Bitcoin. So bear with me. This is a little bit more theoretical than most of the works you see here. But let's just suppose that the program is S bits long. So let's say just 1,000 bits, and the execution is much greater than that. Maybe it takes 1,000,000 steps. Okay? So the minimal possible costs on both sides. Alice must at least send the program to Bob, and that's going to be at least 1,000, bits worth of work. And Bob must at least execute it, because otherwise we'll be contradicting the undecidability of the halting problem. So Bob must run for time at least T, and then he responds to Alice. And what we achieve in our system is very close to that. So the cost to Alice is going to be very close to S. It's going to be a small polynomial in S, and we'll have benchmarks to see how small it is. But it's really quite efficient. And the cost to Bob is, again, very close to T log T. It's going to be something like T times log T squared or cubed. And again, we'll have benchmarks to see how it works. So how do we do it? You're probably trying to think, well, how do I sign it? So you're thinking, well, let's take a hash or something like that, right? And this is something that, say, antivirus programs do, right? You take a large file and then you compress it into some cryptographic hash and you sort of send that, right? And then, if someone wants to mess with a program and change the binary in any way, then the hash just won't align with that. Well, it's a good start, but it's a long way to the actual solution. And the reason is that what we're really signing is not a binary of a program, but a whole trace of an execution. And we have to check that every step in the execution worked well and sign that. So it's a much more complicated kind of cryptographic signature. Okay? So in particular, it's all available on my web page. It's all publicly available. You can read it. It's going to be hundreds of pages of advanced theoretical computer science, but I encourage you to read at least the introductions and see some of the talks on it. But the point I want to get over to you is that it's a little bit like the case of the fast Fourier transform and other very advanced algorithms, where the mathematics that underlies it is very complicated and making progress on it is very hard, but at the end of the day it translates, like the FFT, into very efficient algorithms that you can, say, run on your mobile app. In the case of FFTs, when you're listening to music or downloading a movie, there's a lot of FFTs going behind the scenes. The math is very complicated, but the implementation turns out to be rather sweet. So it's the same in our case. And as I said, our system uses a lot of very famous works, just huge breakthroughs in theoretical computer science, and I encourage you to look a little bit into more about that. There are a lot of Wikipedia pages describing these things, such as probabilistically checkable and computationally sound proofs and so on. Before I tell you a little bit how the system actually looks and works, let me tell you who are we. It's not myself. We have a pretty big team. It started with a very nice grant that I received from the European Research Council in 2009. And we used this grant together with my co-leader, Professor Eran Tromer from Tel Aviv University. We started to implement it in the summer of 2010. And the first thing was to scale this lofty theory down to practice. That led to a number of publications, again, available. And we did some work there. And now we're starting, over the years, we started to implement it. And we have a pretty large team working on it, which sits all over the place. There's a large team at Technion. A bunch of us are sitting at MIT, including myself right now, and Tel Aviv University. And we have ongoing meetings by Skype and so on, so it's just picking up pace. So in terms of, say, things to look for in the Bitcoin world, if you want to try and play with this, phase one, which I'll describe soon, is going to appear within a few weeks. We have a hard deadline of presenting it at the conference on cryptography that's going to be in Santa Barbara in August. You're all welcome to come and see it. And we'll put things online hopefully much before that. So by the end of August there'll be some documents and some source code to look at. This phase one will have an initial setup cost to run the system for a particular program of roughly T log T. And I'll show you in a minute how it's going to work. And the cost to Bob is going to be T log T, where T is the running time of the program. But the cost for Alice to verify, again, integrity of a computation in a way that doesn't compromise the privacy of Bob's private auxiliary inputs is going to be really minimal. This is going to be like, downloading 10 kilobytes even for a very long program. And maybe this will do it. Sorry. And verifying will take something like a second or order a few seconds on a mobile app. And phase two later in the summer is going to have the costs for both Alice and Bob completely optimal. So let me just show you how the system is going to work in phase one, again coming in a few weeks. You'll start with an arbitrary C program written in some standard version of C, C99 or something like that. And the first thing you'll do is throw it through a new compiler, a new GCC backend that we wrote. And out you'll get assembly code for a new machine specification that, again, the specification is going to come online. So you get assembly code. This is just like a standard, the standard way that you work with any program these days, right? Now comes the new stuff. In this pre-processing phase, which in the case of Bitcoin could be set up by the Bitcoin, I don't know what the central authorities are, but for any computation that is deemed important enough, someone will do this pre-processing phase. And in this pre-processing phase, you take the assembly code, you take a bound on the running time of the program, and you take some auxiliary randomness used for cryptographic purposes. You throw it into a cryptographic engine, which is the main thing in our work, and out come two things. One is the prover's key, and the other is the verifier's key. The prover's key is pretty long. It's as long as the computation, but the verifier key is really, really short. So now the prover gets the prover key, and it can be posted, for anyone to use. And the verifier will get the verifier key. So for instance, for the prover key, if this is proving all transactions or the last block that it's consistent, this will probably go to the nodes, and they'll just have it there always to use when they're signing their latest work. And the verifier key, which is very long, could also be posted, and anyone can just download it onto their mobile app. Or this will just be part of the client sitting there. And the prover will get the input, could be the block, the latest block in the blockchain, all of the blockchain, and the prover's key, and will do a computation which essentially runs through the execution of the C program and signs it. So out will come an output, which should always come out, and a signature. The signature reveals nothing but for the correctness of the output of the program. So even if a single bit in the execution is by mistake or maliciously changed, the signature won't match up. And Alice will have a very easy task of verifying this thing. That's phase one. Phase two is even sweeter. The pre-processing is really just compiling the program, into this new assembly code that we have. And this can be done by anyone. It can be done by Alice because it's so easy, by Bob, or by the system. Now the prover will execute it, and will send again the output and the signature, which Alice will verify at very minimal cost. So this is really as lean, as asymptotically good that you can hope for. And this hopefully will be by the end of the summer. So just a little bit of numbers again in the context of Bitcoin, and I just should say that these numbers are going down all the time. So this is not the end point, this is the start point. Our main measure of efficiency is there are constraints generated. Basically, the prover just has to prove that a whole lot of constraints all match up. Every step of the computation was okay, and in a cryptographic way then compress it into a signature. Okay? So the main measure of efficiency is going to be the number of constraints, and right now we can just verifying a single step of our abstract virtual machine, which say takes 16 registers with 32 bits. So it's a pretty powerful kind of framework. You have quite a lot of registers there, and I should mention that you of course have random access memory. So you have a whole lot of memory out there, but you can run a lot of things inside the memory. That's going to cost you about 1,500 constraints per one machine cycle. And we did a back-of-the-envelope calculation showing that if you want to verify a single SHA-256, it's going to take you currently around 20K constraints. And we're already playing with systems that handle between something like around 4 million constraints, and we're going to boost it up pretty soon to 30 million constraints. And our only limitation is the RAM limits that we have on the machines that we are, that are currently available to us. We haven't bought any specific hardware to deal with it, but this is completely scalable. You just need more memory and to fit the whole thing inside. So the bottom line would be that if you want to have computational integrity and privacy for some simple C programs that would also include roughly 1,000 op SHA-256, then this is something that within a few weeks we should be able to do. So looking ahead, suppose Bitcoin likes this project, and I hope they do. I think they should. Suppose, bear with me for a minute, that at some point in the future, Forth-like script is allowed to be replaced with C, which could be a good idea for a lot of reasons. And even if not, you could just have this as something that builds upon the basic Bitcoin protocol. Then you could use our system to guarantee privacy and integrity, and there's a whole range of things that you could do with that. You could get untraceable proofs of payments and proofs of ownerships. You could get untraceable auditing, again, verifying all kinds of things about your history for tax purposes or whatever it is without revealing any information about the actual coins that you own and so on. This could also be good for receipts, for merchants, to have like tangible proofs that someone paid something without revealing any information about them. You could do things like exchanges and contingent payments and future contracts in a much simpler way. Again, because you'll just be writing C code. And here I want to thank Greg Maxwell for raising this idea of contingent payments to use zero knowledge and computational integrity and privacy for it. Greg, there you are. Thanks. Okay, we should chat afterwards. And you could also boost anonymity by, so you all saw that there's this really spectacular work about the zero coin protocol, and using our system you could do similar things of anonymizing, taking a lot of coins into a big pool and distributing them into a way that you never know which coin came from which coin here went to which address there. You could do it in a more seamless way by writing the proper C code that basically adds up the coins, proves that it knows of 1,000 addresses. Here are the addresses. They went pooled into one place and then they got distributed, and all you learned is that everything matches up, but you don't know which input goes to which output. Okay, so that's another thing you could do. So if you want to learn more, if you want to learn more, first of all, on Tuesday, 2 days from now, 4:30, I'm giving at Stanford Security Seminar, I'll be giving a talk that will be a little bit more technical, and we'll tell a little bit more about how we do the theory. You could also watch my previous talk. I'll put these slides, so you'll have the hyperlinks and to this talk that I gave at Stanford, again, with pretty much the same ideas, going a little bit more under the hood. Also, you're welcome, again, just all of these conferences happen to be taking place very close by. June 3rd, that's like in a week and a half, there's going to be a presentation of our work at one of the main conferences on theoretical computer science. It's called please come there. And at Crypto in Santa Barbara at August, we'll have more implementation demos running. You can read our recent papers. And I just want to finish by saying that if you want to use this, please, look me up here at the conference or send me an email, talk to me. Thanks a lot.
So the VM is clear to verify. Is there some translation between this and expression reduction languages like Lisp or Haskell?
I'm not sure I understood the question.
Expression reduction, Lisp-like languages.
Right now we're writing it for C.
Yes.
There's nothing that prevents doing exactly the same thing for Lisp or any other programming language. Does that answer the question?
It kind of answers the question. Clearly, Lisp can be run on a VM.
Right.
The question is really, is there a more native translation for those languages? I'll work on that.
Yeah, but right now we haven't written it, but it should be doable, and we can discuss this offline. Yes.
In the phase 1 section back there, where you're pre-computing the prover's key and the verifier's key. Are those keys sensitive to program inputs, or is that just sensitive to the program itself? I.e., if I'm pre-computing this massive setup, can I pre-compute that for a general program, pass it out, and people can pass arbitrary inputs into it, or do I have to recompute for every input?
No, you don't.
Okay. Awesome.
Okay, I think I'm getting a signal that our time is up, so we'll take it offline. Okay, thanks a lot.